In this lesson, we survey the various forms of reduction used throughout organic chemistry, including hydrogenations, hydride donors, and other reductions. Organic reductions can be categorized into three general types: hydrogenations, reductions using hydride donors, and other miscellaneous reactions. First up, we have hydrogenations. Hydrogenation is the addition of hydrogen gas across a pi bond and is mostly used to reduce pi bonds that are not particularly polarized. The reaction requires a particular metal catalyst such as palladium, platinum, or nickel. The most common use for hydrogenation is the reduction of carbon-carbon pi bonds. In the first example, we see the reduction of an alkene to an alkane. You can see that one hydrogen atom is added to each carbon of the carbon-carbon pi bond. Next, we see the reduction of an alkyne to an alkane via two sequential hydrogenations. Remember that the hydrogenation of an alkyne using a common catalyst like palladium cannot be stopped after a single addition. In order to reduce an alkyne to an alkene, a special poisoned catalyst like Lindlar's catalyst must be used. Lindlar's catalyst is actually a form of palladium that's been made less reactive by the inclusion of additives like lead and quinoline. In the last example, we see an alkyne reduced to an alkene via Lindlar hydrogenation. Remember that hydrogenation is syn stereoselective and will provide cis alkenes from the reaction of internal alkynes. Hydrogenation can also be used to reduce certain slightly polarized pi bonds. The hydrogenations of nitrogen-containing functionalities like nitriles, imines, and nitro groups are fairly common. In the first example, we see a nitrile reduced to an amine via two sequential hydrogenations. In the product, you can see that two hydrogen atoms have been added to both the carbon and nitrogen of the triple bond. Next, we see an imine also reduced to an amine using hydrogenation. In the next example, we see the hydrogenation of a nitro group. The reduction of nitrobenzenes is an important method for the preparation of anilines. Hydrogenation is not typically used to reduce carbonyls, even when very powerful catalysts are used. Here we see an example of a failed hydrogenation of an ester, even when using raining nickel, a special and very potent hydrogenation catalyst. Extremely reactive carbonyls like acyl halides can, however, be hydrogenated. In this example, we see acetyl chloride reduced to ethanol via hydrogenation using raining nickel. In the last example, we see the hydrogenation of an acyl halide using the Rosenmund catalyst, another special poisoned catalyst similar to Lindlar's catalyst. The reaction is unusual in that it produces an aldehyde. If you look back at all the other hydrogenations of CN and CO pi bonds, you'll notice that in each case the carbon ended up at the first redox level, having only one bond to an electronegative atom. As you'll see, this is true for other forms of reduction as well. Reduction of CN and CO pi bonds usually ends up with the carbon at the first redox level, typically forming an alcohol or an amine. Stopping a reduction at the second redox level, as we see here, is synthetically very useful but also very challenging since the product could easily be reduced further. The next category of organic reductions are those that use metal hydrides or hydride donors. Hydride donors can be thought of as sources of H- or hydride, and are useful for reducing more polar pi bonds, particularly the CO pi bonds of carbonyls. The most common hydride donors are sodium borohydride and the more powerful lithium aluminum hydride. In the first example, we see the reduction of a ketone with sodium borohydride to give an alcohol. In general, sodium borohydride can only be used to reduce aldehydes and ketones, and not other, less reactive carbonyl types. Aldehydes and ketones can also be reduced using the more powerful lithium aluminum hydride. Remember that lithium aluminum hydride is incompatible with protic substances like water and alcohols, and the reaction must therefore be quenched with acid in a second, later step. Lithium aluminum hydride can be used to reduce any carbonyl type. Here, we see an example of an ester reduced with lithium aluminum hydride to give an alcohol. In the last example, we see an amide reduced with lithium aluminum hydride to give an amine. Remember that reductions of nitrogen-containing functional groups like amines and nitriles typically result in the formation of an amine and not an alcohol. Also notice that in all four reactions, the carbon ends up at the first redox level, forming either an alcohol or an amine. Some carboxylic acid derivatives can be reduced to aldehydes using special hydride donors, stopping the reduction with the carbon at the second redox level. The most commonly used hydride donor for this purpose is DIBA, diisobutyl aluminum hydride, shown here. In this example, we see an ester reduced with dibond to give an aldehyde. The reaction must be performed at a very cold temperature, which allows the reagent to bind to an oxygen atom after the first addition of hydride. This suppresses the normal acyl substitution pathway and prevents a second reduction from occurring. Another special hydride donor is lithium triterpenoxy aluminum hydride. This reagent can be used to selectively reduce acyl halides to give aldehydes. In this example, we see acetyl chloride reduced to acetaldehyde using this reagent. The final category of organic reductions is a bit of a catch-all and includes reactions that don't really fit into any other category. The first of these other reduction types is deoxygenation. Both aldehydes and ketones can be deoxygenated, replacing the oxygen with two hydrogen atoms. Keep in mind that other carbonyl types like esters and other carboxylic acid derivatives cannot be deoxygenated. The two most important deoxygenation reactions are the Wolff-Kishner reduction and the Clemmensen reduction. The Wolff-Kishner reduction is effected using hydrazine and base. In this example, we see acetone deoxygenated to give propane. The Clemmensen reduction uses a zinc-mercury amalgam under acidic conditions to achieve the same transformation. In the example, we again see acetone deoxygenated to give propane. The hydrogenolysis of thioketals using raining nickel can also be considered a net deoxygenation. Remember that thioacetals and thioketals are prepared from aldehydes and ketones via reaction with excess thiol under acidic conditions. The last reduction we'll take a look at is the metal ammonia or dissolving metal reduction. Internal alkynes can be reduced to alkenes by dissolving certain metals such as lithium or sodium into liquid ammonia. In the example, we see 2-butyne reduced to give trans-2-butene. The reaction is anti-stereoselective, giving trans alkenes, and provides a stereochemical complement to the linear hydrogenation of alkynes. Remember that the reaction only works on internal alkynes. Terminal alkynes are deprotonated to form acetylide ions under these conditions, suppressing the reaction.